Our modern world runs on brilliant mathematics, yet the Great Pyramid of Giza was built with a precision that challenges modern engineering. This was not magic. It was advanced math. We are about to journey across millennia to uncover 35 ancient civilizations who possessed mathematical knowledge so sophisticated it would baffle many people today. You will discover the hidden formulas and forgotten genius that built our world. How did cultures separated by oceans and deserts solve complex equations we thought were modern inventions? What does it say about human ingenuity that these discoveries happened not once but over and over? Are you ready to meet the original mathematical masters? Long before the pyramids rose from the sands of Egypt, another civilization was laying the foundation for our modern world in the Fertile Crescent of Mesopotamia. The Sumerians, building their vast city-states between the Tigris and Euphrates rivers, did not just invent writing. They engineered one of humanity's first and most enduring mathematical systems. Their choice of base 60 seems strange to us today who count in tens, but its brilliance is etched into our daily lives. Every time you check a clock, you are reading a Sumerian innovation: 60 seconds in a minute, 60 minutes in an hour. Look at a circle and you see their legacy again in its 360 degrees. Why 60? It is a highly composite number, easily divisible by 1, 2, 3, 4, 5, 6, 10, 12, 15, 20, and 30. This made complex calculations for trade and construction far simpler, but this was not just abstract theory. Sumerian scribes used this system to manage immense economic complexity. They calculated interest on loans, determined the area of fields after the annual floods reshaped the land, and allocated rations for thousands of workers. They pressed these calculations into wet clay tablets, creating a permanent record of their numerical genius. Some of these tablets are not simple accounts. They are sophisticated mathematical texts, posing and solving geometric problems about dividing up land, and even working through what we would now call quadratic equations. This formalized approach to math was the administrative backbone of their society, allowing them to build, trade, and govern on a scale never before seen. It was the essential tool that turned a collection of cities into the world's first civilization, proving that mathematics and empire grew together from the very beginning. While the Sumerians were perfecting their base 60 system, another civilization was mastering a different kind of mathematical precision on the banks of the Nile. The ancient Egyptians built monuments that still defy easy explanation, and their mathematical genius was the invisible blueprint for these stone giants. The sheer scale of the Great Pyramid is staggering, but its true wonder lies in its impossible accuracy. Its base is almost a perfect square, with sides aligned to the cardinal directions with an error of less than 1/15 of a degree. This was not achieved by guesswork. It was the result of a sophisticated and practical mathematical tradition. For slopes, they used a unit called the sek. This was the horizontal distance for a drop of 1 cubit, a simple yet brilliant concept that allowed them to design and build the iconic pyramid shape with unwavering consistency across millions of stone blocks. Their mathematical needs were born from the rhythm of the Nile itself. Each year, the river would flood, wiping away the boundary markers between fields. To restore order, a special class of surveyors known as the rope stretchers would arrive. With ropes knotted at precise intervals, they could remeasure the land, calculating areas and dividing plots using practical geometry. This was mathematics in service of society, ensuring a fair and functional agricultural system. We know the details of their methods from surviving texts like the Rhind mathematical papyrus, a scribe's training manual filled with problems. They had a deep understanding of fractions, which were essential for distributing grain and supplies. They performed arithmetic, algebra, and could calculate the volumes of granaries and the areas of fields. One famous problem even calculates the slope of a pyramid. proving the seeked was a standard tool in their intellectual kit. This was not abstract theory for them. It was the essential, applied science that built a civilization capable of reaching for the sky. Far to the east, the Indus Valley civilization achieved a different kind of mathematical perfection. Their great cities, Mohenjo-Daro and Harappa, were marvels of urban planning laid out with a geometric precision that rivals modern grids. Wide, straight streets ran in perfect north-south and east-west alignments, intersecting at right angles to create entire city blocks. This was not an organic growth of alleys and paths. It was a master plan executed on a colossal scale, requiring an advanced understanding of geometry and measurement to survey the land and plot the foundations for thousands of buildings. The very bricks that built this civilization tell a silent story of standardization. Across an area larger than ancient Egypt or Mesopotamia, every fired brick adhered to a universal ratio of 4:2:1 for its length, width, and height. This consistency meant a brick from the northern reaches of the civilization would fit perfectly with a brick from the southern coast. Such uniformity points to a centralized system of weights and measures, a common mathematical language understood by all. This language appears to have been based on a decimal system. Archaeologists have discovered carefully crafted stone weights that progress in a decimal fashion, doubling from 1 unit to 2, then 4, then 8, and so on. This logical progression made trade and commerce incredibly efficient, creating a stable economic foundation for their society. Their mathematical mind is also visible in the small, intricate seals used for branding trade goods. These seals are covered with complex geometric patterns and depictions of animals, all rendered with a profound sense of symmetry and proportion. This artistic precision was not merely decorative. It was the hallmark of a culture that thought in ratios and balanced forms, applying mathematical principles to everything from the grand scale of their city plans down to the smallest artifacts of daily life. The Indus Valley people left behind no grand pyramids, but their legacy is a testament to the power of mathematical order in creating a stable, thriving, and interconnected world. Built on the island of Crete, the Palace of Knossos was a labyrinth of mathematical genius. This was not a simple collection of buildings but a multi-story complex so advanced its plumbing would not be matched for over 1,000 years. Intricate terracotta pipes, designed with precise gradients, formed a sophisticated drainage and water supply system that snaked through the walls. Creating such a network required a masterful grasp of engineering mathematics and volume calculations to ensure water flowed consistently and powerfully without bursting the conduits or stagnating in pools. This was hydraulic engineering on a grand scale, all accomplished by a civilization that flourished over 3,500 years ago. The Minoans left behind clay tablets inscribed with their own numerical system, a script we can partially read but whose full linguistic meaning remains tantalizingly out of reach. The numbers themselves, however, are clear, showing they used a decimal system with distinct symbols for units, tens, hundreds, and thousands. This structured approach was essential for administering their vast maritime trade empire, tracking the movement of goods like pottery, olive oil, and textiles across the entire Mediterranean. Their mathematical mind is perhaps most beautifully expressed in their art. The vibrant frescoes that adorn their palace walls are a symphony of geometric order. Spirals, interlocking patterns, and rhythmic motifs repeat with perfect symmetry, revealing an intuitive yet calculated understanding of proportion. Even their pottery, from massive storage jars to delicate cups, showcases forms balanced with such harmony that they could only have been conceived by artists who thought in ratios. This pervasive sense of geometry was likely more than just aesthetic. The same principles that guided their brushstrokes would have been critical for celestial navigation, allowing their ships to traverse the open sea by reading the stars. The Minoans proved that mathematics was not confined to ledgers and blueprints. It was the invisible current that flowed through their pipes, defined their art, and guided their ships, a seamless integration of calculation and culture that made their civilization a beacon of the ancient world. As the Minoan world faded, a new power rose on the Greek mainland, one whose mathematical mind was expressed not in elegant plumbing but in colossal, unmovable stone. The Mycenaeans built for war and eternity, and their so-called Cyclopean walls at cities like Mycenae were a feat of terrifying engineering. These fortifications were made from enormous limestone boulders, some weighing many tons, fitted together without mortar. The sheer mass was only part of the story. The true genius lay in the precise calculations required for stability. Each irregularly shaped stone had to be carefully selected and positioned so that its weight and the angles of its faces distributed the immense load perfectly, creating a structure that could withstand sieges and earthquakes for millennia. The famous Lion Gate stands as a monumental proof of their skill, its massive lintel stone precisely calculated to bear the weight of the wall above without cracking, a silent testament to their understanding of force and counterforce. This same calculative precision governed their administration, revealed to us through the clay tablets inscribed with Linear B script. This was not a language of poetry or myth, but one of rigorous accounting. The Mycenaeans used a straightforward decimal number system, with distinct symbols for units, tens, hundreds, and thousands. Their scribes meticulously recorded everything from counts of chariot wheels and bronze spearheads to vast holdings of grain, olive oil, and livestock. One tablet might list over 10,000 sheep across different regions, while another details the exact acreage of royal estates. This was mathematics as the backbone of a palatial economy, requiring fluent arithmetic to manage resources, levy taxes, and supply a powerful military. The numbers were not abstract, they were the vital statistics of a civilization, and their survival depended on getting the math right. Perhaps their most mathematically daring structures were not their fortresses, but their tombs. The Tholos tombs, like the magnificent treasury of Atreus, showcase an early and breathtaking application of architectural geometry. These were not simple holes in the ground, but vast, circular burial chambers with soaring corbelled domes. To construct such a dome, each successive ring of stone blocks had to be cantilevered slightly inward, a process requiring an exact and consistent calculation of the overhang for every single stone course. A single miscalculation in the geometry of the curve would have caused the entire dome to collapse under its own weight. The result was a perfect beehive-shaped vault that remained the widest unsupported dome in the world for over 1,000 years. In these silent, underground spaces, the Mycenaean grasp of form, pressure, and geometric progression achieved a kind of immortality, proving that their mathematical legacy was carved as deeply into the earth as it was into their administrative records. The mathematical torch first lit by the Sumerians was carried to even greater heights by their successors, the Babylonians. They perfected the base 60 system, transforming it into a tool of breathtaking power and abstraction. Their mathematical records, pressed into soft clay with a stylus, reveal a mind capable of grasping relationships we would not formally name for over 1,000 years. Consider the tablet known as Plimpton 322. It is not a list of goods or a tax record, but a table of numbers. To the untrained eye, it is just a grid of figures. But to a mathematician, it is a revelation. This ancient ledger contains a list of what we call Pythagorean triples, sets of 3 whole numbers that perfectly describe the sides of a right triangle. The Babylonians were not just aware of this geometric principle, they were using it systematically long before the Greek philosopher Pythagoras was even born. This was not a lucky guess. It was a sophisticated, documented understanding of one of geometry's most fundamental truths. Their genius extended far beyond geometry into the realm of algebra. Babylonian scribes developed a procedural method for solving what we now call quadratic equations. They did not use symbols like x and y. Instead, they followed step-by-step recipes, a series of instructions that would reliably lead them to the correct answer for problems involving areas and quantities. These were not simple drills. They were complex problems that could determine the dimensions of a field or the outcome of a financial agreement, solved with a logical consistency that feels remarkably modern. In one stunning example, they calculated the value of the square root of 2. Their approximation was accurate to 5 decimal places by our modern counting. How did they achieve such precision without calculators or computers? They used an iterative method, a repetitive process of estimation and refinement that honed in on the answer with incredible accuracy. This was not mere arithmetic, it was a conceptual leap toward the infinite. This mathematical prowess found its ultimate expression in the night sky. The Babylonians were master astronomers, and they developed a complex mathematical machinery to predict the motions of the moon and planets. They created detailed ephemerides, tables that forecast celestial events like lunar eclipses and the positions of planets with remarkable reliability. They did this by meticulously recording observations over centuries, identifying patterns, and then modeling those patterns with numerical sequences and algebraic relationships. This was not astrology in the simple sense. It was a rigorous mathematical science born from the belief that the cosmos operated on predictable, calculable principles. This vast body of knowledge, this fusion of advanced math and precise observation, would later travel west to influence Greek thinkers and east to inspire Islamic scholars, forming a crucial bridge in the history of human thought. The Babylonians looked at the heavens and saw not just gods but a clockwork of numbers, a cosmic order they could capture in the grooves of a clay tablet. High in the rugged highlands of Anatolia, the Hittite Empire forged a dominion of iron and law. Their power was built not just on military might, but on a rigidly organized system of administration that demanded mathematical precision in every facet of life. The very concept of justice was quantified in their legal codes, where crimes and their punishments were meticulously calculated in silver shekels and specific measures of grain or land. This required a universally accepted system of weights and measures across their sprawling empire, ensuring that a payment decreed in the capital, Hattusa, held the exact same value in a distant province. Fair trade and stable land distribution were the bedrock of their society, and both were impossible without a shared mathematical language understood by every merchant, tax collector, and judge. This practical need for standardization fueled their most legendary achievement, the mastery of iron. While other empires worked with bronze, the Hittites unlocked the secrets of smelting iron ore, a process that was less a mystical art and more a feat of extreme thermal mathematics. To produce workable iron instead of a useless, brittle slag, they had to maintain a furnace at a precise, high temperature for an exact duration. This required an intuitive yet advanced understanding of ratios, carefully balancing specific amounts of charcoal to ore and controlling airflow to create a consistent and controllable heat. Their smiths were, in effect, early chemists and engineers, performing complex calculations with fire and raw materials to create the weapons and tools that gave their empire an unshakable advantage. This same calculative mindset was etched into the very landscape of their capital. The massive, sloping walls of Hattusa were not just piles of stone, they were a masterpiece of defensive geometry. The Hittites constructed their fortifications with projecting towers and strategically angled gateways, designed to expose any attacking force to overlapping fields of fire from their defenders. Building these immense, multi-layered ramparts required a deep practical knowledge of geometry and load-bearing engineering to ensure the walls would not collapse under their own weight or the impact of siege engines. The city's layout itself, with its meticulously planned water reservoirs, grain silos, and access roads, was a lesson in logistical mathematics designed to sustain a large population through both peace and protracted war. The Hittite legacy demonstrates that mathematics was the essential tool for turning raw materials, whether legal, metallic, or stone, into the foundations of an imperial power. Across the Atlantic, in the humid lowlands of ancient Mexico, the Olmecs were building a legacy in stone and time. Known as the mother culture of Mesoamerica, their mathematical innovations laid a foundation that would influence civilizations for centuries. Their most profound intellectual leap was the conceptualization of nothingness, the idea of zero. This was not merely a placeholder but a number in its own right, a full-fledged mathematical entity that they used within their sophisticated long-count calendar. By giving a value to emptiness, they could perform complex calculations that tracked vast cycles of time with an accuracy that still inspires awe. This abstract thinking was the engine of their cosmos, allowing them to chart the movements of planets and predict celestial events that governed their rituals and their understanding of the universe. This same sense of cosmic order is carved into the earth at their great ceremonial centers. San Lorenzo and La Venta were not random collections of mounds and plazas. They were precisely engineered landscapes, their central axes and major structures aligned to significant astronomical events like the solstices or the path of Venus. To achieve this, Olmec planners needed a deep, practical command of geometry, using sight lines and measured distances to orient their entire world with the heavens above. The layout was a physical manifestation of their belief system, a giant stone calendar that connected their society to the rhythms of the cosmos. Their mathematical prowess is most viscerally apparent in the colossal stone heads that have become their enduring symbol. Carved from single blocks of basalt, some weighing over 20 tons, these monumental sculptures present a staggering logistical puzzle. The basalt quarries were located dozens of miles away from the ceremonial centers, across rivers, swamps, and challenging terrain. Transporting these multi-ton monoliths required more than just raw manpower. It demanded brilliant logistical mathematics. How many workers were needed to move a single head? How were rollers or rafts deployed most efficiently? The Olmecs had to calculate friction, weight distribution, and the strength of their materials to orchestrate these incredible journeys, turning raw stone into regal portraits through a triumph of collective calculation. Every massive head is a silent testament to a society that could not only conceive of zero, but could also move mountains with the power of their math. Far to the east, another civilization was developing a mathematical language that would endure for millennia. The Shang dynasty, China's first historically confirmed royal line, inscribed their genius onto oracle bones and cast it into bronze. Their mathematical system was decimal and used a place value concept, a revolutionary idea where the position of a digit determines its value. This is the very same foundational principle our modern number system relies on. They had distinct symbols for the numbers 1 through 9, and then separate symbols for tens, hundreds, thousands, and so on. This allowed them to express any number, no matter how large, with remarkable efficiency and clarity. This was not just for counting, it was the administrative engine of a powerful state, used to record troops, tributes, and the vast stores of the royal treasury. This numerical precision was literally carved into history on the so-called oracle bones. These were animal bones or turtle shells that Shang diviners would heat until they cracked, then interpret the patterns to answer the king's questions. The inscriptions record the queries and the outcomes, and they are filled with numbers. They documented the count of sacrificial animals, the number of prisoners taken in battle, and even the days and cycles of the lunar calendar. Some bones contain records of astronomical events like lunar eclipses, demonstrating that their numerical system was also a tool for mapping the heavens and marking the passage of time with mathematical exactness. This calculative mind found its most spectacular expression in the creation of ritual bronze vessels. The process of casting these intricate objects was a feat of applied mathematics and chemistry. Artisans had to create precise clay molds, often in multiple interlocking sections, to form the vessel's complex shape and the elaborate tauti masks and geometric patterns that adorn them. The geometry of these molds had to be perfect, or the molten metal would leak or the final piece would be misshapen. Furthermore, the bronze alloy itself was a mathematical recipe. Achieving the desired strength, color, and resonance required meticulously calculated ratios of copper, tin, and lead. A slight miscalculation in the formula would result in a brittle, flawed vessel, a catastrophic waste of precious resources. The fact that so many of these stunning works survive in perfect condition is a testament to the Shang mastery of metallurgical mathematics. This same sense of order and measurement shaped their world on a grand scale. Their cities, such as the great capital at Anyang, were not haphazard settlements. Archaeological excavations reveal foundations of palaces and royal temples arranged on a north-south axis, with buildings positioned according to a master plan. This deliberate layout reflects a standardized system of measurement and a clear understanding of geometric planning, creating a physical environment that mirrored the cosmic and social order they believed in. Even their royal tombs were mathematical statements, deep rectangular pits constructed with precise dimensions and orientations, designed to house the king and his vast retinue of treasures and sacrificed retainers for the afterlife. From the micro-scale of a bronze recipe to the macro-scale of a city plan, the Shang dynasty proves that mathematics was the invisible framework upon which their entire civilization was built. While the Shang were casting their bronze vessels, an entirely different mathematical tradition was flourishing in the ancient Indian subcontinent. The Vedic civilization wove numbers and geometry directly into the fabric of the cosmos through their sacred texts, the Vedas. These were not merely philosophical or religious works, they were also profound mathematical manuals. Their most explicit mathematical knowledge is found in the Sulba Sutras, a series of appendices that provided the precise geometric rules for constructing the complex fire altars central to Vedic ritual. The correct performance of a sacrifice, and thus the maintenance of cosmic order, depended on the altar being built to an exact shape and area. A single miscalculation in its dimensions was believed to render the entire ritual void. This spiritual necessity drove an incredible precision in practical geometry. The Sulba Sutras contain clear instructions for constructing squares and rectangles, for transforming one geometric shape into another of equal area, and even for building a square with an area equal to the sum of two other squares. This is nothing less than a statement of the Pythagorean theorem, written centuries before Pythagoras himself. The Vedic seers did not just know the rule, they provided step-by-step methods to implement it with ropes and stakes, turning abstract principle into tangible, sacred architecture. Their mathematical insights reached even further into the abstract. They displayed a clear understanding of irrational numbers, offering remarkably accurate approximations for the square root of 2. One sutra gives a value that is correct to 5 decimal places, a stunning feat of calculation for its time. They also explored concepts of prime numbers and articulated basic algebraic identities, like the rules for expanding a sum multiplied by itself. This was a mathematics born from a deep, spiritual need to measure and map the universe. The altars were designed as microcosms, their areas symbolizing the earth, the atmosphere, and the heavens. Building them correctly was a way of aligning human activity with the celestial order, a ritual act that required an advanced grasp of astronomy to time the ceremonies and of geometry to build the stage. This sacred fusion of calculation and cosmos, of number and divinity, created a powerful intellectual foundation. The mathematical seeds planted in the Sulba Sutras would later blossom into the monumental achievements of Indian mathematicians, who would go on to give the world the concept of zero as a number and the decimal system we use today. The Assyrian Empire ran on calculated terror and precision. Their armies were not just hordes of soldiers, they were mobile engineering corps, and their greatest weapon was often mathematics. To breach a fortified city, Assyrian engineers would construct colossal earthen ramps, sloping directly into the heart of enemy walls. This was not a matter of piling up dirt. Each ramp was a massive logistical project, requiring the precise calculation of volume, slope, and material strength. How much earth was needed to reach a wall 50 feet high? How steep could the incline be before it collapsed under the weight of their siege towers? They solved these problems with terrifying efficiency, using math to turn landscapes into weapons. The same calculative genius that conquered cities was used to build them. Their grand capital, Nineveh, was a masterpiece of urban engineering, protected by walls so massive that 2 chariots could ride abreast on their top. Beneath this show of power flowed an even more brilliant system. The city was supplied with water by a monumental aqueduct built by King Sennacherib, a structure that channeled water from over 30 miles away. Its builders used sophisticated gradients and siphons to maintain water flow across hills and valleys, a feat of hydraulic engineering that demanded a deep understanding of geometry and pressure. Inside the city, the royal palaces were decorated with mathematical artistry, their walls lined with carved stone panels measured and fitted with such exactness that the scenes of conquest and ceremony appeared seamless. The true repository of Assyrian knowledge, however, was not in its stones but in its clay. The library of Ashurbanipal, assembled by the last great Assyrian king, was one of the ancient world's first great libraries. Among its thousands of tablets were extensive mathematical texts. These were not theoretical exercises, they were practical manuals for running an empire. Scribes studied tablets filled with problems on calculating compound interest on silver loans, essential for financing military campaigns and long-distance trade. Others detailed the geometric calculations for dividing inheritance fairly among sons, preventing the internal disputes that could weaken powerful families. There were even tables for figuring out the exact amount of earth to excavate for canals or the number of bricks needed for a new fortress wall. Every administrative function, from taxation to troop supply, relied on this standardized mathematical knowledge. The Assyrians proved that mathematics was the ultimate tool of imperial control, the silent partner in every conquest and the invisible architect of every monumental city. To cross the open sea, you need more than a sturdy ship and a brave heart. You need the stars as your map and numbers as your compass. The Phoenicians, the master seafarers of the ancient Mediterranean, possessed this mathematical navigation. Their voyages stretched from the coast of modern-day Lebanon all the way to Britain and possibly around Africa, journeys that would have been impossible without a deep, practical command of astronomy and geometry. They sailed by night using the North Star, which they called the Phoenician Star, as their fixed celestial guide. But a single star is not enough for a precise course. They understood the movements of other constellations, calculating their position and the changing angles throughout the year to determine latitude and plot a reliable path across featureless water. This was not passive stargazing, it was an active calculative science of the heavens. Their reputation for accuracy extended from the sea to the marketplace. Phoenician merchants developed a system of weights and measures so reliable it became the trusted standard across the ancient world. Archaeological finds show their stone weights, shaped like sleeping ducks, conforming to a precise unit known as the shekel. This standardization was the bedrock of their commercial empire. A merchant in Egypt could trust the weight of silver from a Phoenician trader, just as a buyer in Greece could be confident in the volume of wine or olive oil in a Phoenician amphora. This universal trust eliminated haggling over basic measurements and greased the wheels of international trade, creating an economic network held together by mathematical consistency. Their greatest mathematical contribution, however, may have been their role as conduits of knowledge. As they moved goods between Egypt, Mesopotamia, and the emerging Greek city-states, they also transported ideas. It is highly probable that the Phoenician trading posts scattered across the Mediterranean acted as way stations for mathematical concepts. The geometry of the Egyptians and the algebraic traditions of Mesopotamia could have traveled on their ships, carried by scribes and educated merchants who shared practical calculation techniques with their business partners. They were the invisible network that connected the great mathematical minds of the ancient world, ensuring that discoveries made in one civilization did not die there but could cross oceans to inspire another. The Phoenicians themselves left few written records of their own math, but their legacy is written in the success of their voyages and the trust of their trading partners, a testament to a civilization that used calculation to build bridges between worlds. South of Egypt, the kingdom of Kush forged its own mathematical identity in stone and iron. While they were neighbors and often rivals to the Egyptians, the Kushites developed a unique architectural signature most visible in their own pyramids. At the royal necropolis of Meroe, hundreds of these structures rise from the desert, but they are not copies of the Giza monuments. They are distinctly Kushite, built with a much steeper, more sharply angled geometry. This was not a mistake or a regression in skill. It was a deliberate design choice, a different mathematical solution to the same eternal problem of constructing a stable, monumental tomb. The steeper angle required a different calculation for the distribution of weight and the internal structure, a testament to their independent engineering genius. This mathematical mind was not confined to the realm of the dead. It was the driving force behind their economic power. The Kushites became one of the ancient world's foremost producers of iron, and their capital at Meroe was essentially an industrial hub. Smelting iron from ore is not a simple process of heating rock. It is a chemical reaction that demands absolute precision. To produce high-quality metal instead of a useless slag, Kushite metallurgists had to maintain their furnaces at a specific, intensely high temperature for an exact period of time. This required a masterful, if intuitive, grasp of applied mathematics. They were calculating the perfect fuel-to-ore ratio, balancing precise amounts of charcoal against specific quantities of raw ore to create a consistent and controllable environment. A single miscalculation in this thermal recipe would waste days of labor and precious resources. Their furnaces were, in effect, chemical equations made of clay and fire. This same practical intelligence shaped the very land they lived on. In a region where the Nile's floods were less predictable than in Egypt, the Kushites engineered sophisticated irrigation systems to harness the river's power. They constructed complex networks of canals and water-lifting devices like the Shaduf, which required a deep understanding of hydraulics and leverage to move water efficiently from the river to their fields. Calculating the correct gradients for these canals was essential. A slope that was too steep would cause erosion and water loss, while one that was too shallow would result in stagnation. Their survival in a challenging environment depended on getting these mathematical relationships exactly right. This calculative precision extended to their urban planning. The city of Meroe itself was laid out with a clear, organized grid, its streets and residential districts arranged for both efficiency and defense. The placement of temples, palaces, and industrial areas like the massive iron smelting quarters reveals a society that planned its space with a clear, logical purpose, using measurement and geometry to create a functional and powerful capital. The Kingdom of Kush demonstrates that advanced mathematics was not a single, monolithic tradition passed down from Egypt, but a versatile tool that different cultures could master and adapt to build their own unique path to greatness. While the Shang cast their world in bronze, the Zhou dynasty wove mathematics into the very fabric of Chinese statecraft and philosophy. Over their 8th-century reign, mathematical thought became a formalized discipline, essential for governing a vast territory and understanding humanity's place in the cosmos. This intellectual fervor produced one of history's most significant mathematical texts, the Zhu Bai Suan Jing, or the arithmetical classic of the gnomon and the circular paths of heaven. This was not a simple collection of problems, but a profound dialogue on the geometry of the universe. It detailed complex astronomical calculations using the shadow cast by a simple gnomon, a vertical pole, to measure the sun's angle and even calculate the height of the celestial sphere. Within its pages lies one of the earliest known proofs of the Gaogu theorem. This is the Chinese name for the Pythagorean theorem, a clear geometric principle stating that in a right triangle, the square of the hypotenuse equals the sum of the squares of the other two sides. The Zhu by Suan Jing presents a brilliantly visual proof, likely using a diagram of squares and triangles that could be rearranged to demonstrate the relationship with undeniable clarity. This text cemented a mathematical truth that was both practical and cosmic in its implications. The tools of this mathematical revolution were elegantly simple. Zhu mathematicians performed their complex calculations using sets of counting rods. These were small sticks, typically made from bamboo or bone, laid out on a counting board. The rods themselves were not mere markers, they formed a place-valued decimal system. By positioning rods in different columns for units, tens, hundreds, and so on, and by alternating their orientation for odd and even powers of 10, they could represent any number and perform sophisticated arithmetic operations, including fractions and even what we would now call algebra. This physical, tactile system was the engine behind the dynasty's administrative machinery. The state's survival depended on a fair and accurate land tax system, which required officials to constantly survey fields, calculate their areas regardless of shape, and convert those areas into standardized tax quotas. All of this was done with counting rods, turning the geometry of the land into the revenue of the empire. This calculative precision reached into every aspect of high culture. The Zhu calendar was a masterpiece of mathematical astronomy, a complex lunisolar system that had to reconcile the cycles of the moon with the solar year. This required precise observations and calculations to periodically intercalate or insert extra months, ensuring that the seasons and festivals remained in sync with the celestial clock. A miscalculation could throw the entire agricultural and ritual cycle into chaos. Mathematics even dictated the arts. The creation of the standardized bronze bells used in court rituals and music was a feat of acoustic engineering. The precise pitch of each bell was determined by its physical dimensions, a strict mathematical ratio between its height, width, and thickness. Craftsmen had to calculate these measurements with incredible accuracy before a single mold was made because the tone was cast into the metal itself. A beautiful sound was not just an artistic achievement, it was the product of perfect mathematical harmony, a physical echo of the order they believed governed the universe. Before the Roman legions marched, the Etruscans mastered the Italian landscape with a geometry of divine order. Their cities did not grow by accident, they were formally founded in a ceremony known as the Ritus Etruscus. A priest would harness a bronze plow to a white ox and trace a sacred boundary, a perfect rectangle aligned with the cardinal directions. Within this ritual perimeter, a grid of streets was laid out with immaculate precision, creating two main avenues that crossed at the city's heart. This was not just urban planning, it was a form of cosmic mathematics, dividing the terrestrial world into a mirror of the celestial realm, a physical manifestation of their belief that human order must reflect the order of the gods. The entire city became a giant geometric altar, its foundations calculated to secure the favor of the heavens. This same calculative genius ran beneath their feet in a labyrinth of tunnels called cuniculi. These were not simple ditches, but complex feats of hydraulic engineering designed to drain marshy land, control water tables, and channel fresh water. Building a cuniculus required a profound understanding of gradients. The engineers had to calculate a consistent, gentle slope over long distances, often beginning from a vertical shaft dug deep into the earth. A miscalculation of even a fraction of a degree would mean the water would either flow too slowly and silt up, or too quickly and erode the tunnel walls. They achieved this with astonishing accuracy using simple tools like sighting poles and water levels, demonstrating a practical mastery of trigonometry that transformed unhealthy swamps into fertile, habitable land. Their mathematical language was etched into their numeral system, a set of symbols the Romans would later adopt and spread across their empire. The Etruscans used a tally-like system where 1 was a single stroke, 5 was a V shape, and 10 was an X. While not a place value system, its clarity and efficiency for recording counts of goods, marking boundaries, and inscribing calendars made it a powerful tool for administration and trade. This mathematical thinking permeated their most personal spaces, their tombs. The vast necropolises carved into the rock at places like Servatory are cities of the dead, their circular tumuli and rectilinear streets echoing the precise layouts of the living world. Inside, the chambers are proportional marvels with beams and lintels carved in perfect imitation of wooden architecture, their dimensions based on harmonious ratios. This sense of sacred geometry extended to their renowned metalwork. Etruscan craftsmen produced breathtaking bronzes from life-sized statues to intricate mirrors. The mirrors were not just reflective surfaces, they were discs of mathematical art. Using a compass and straightedge, artisans would engrave the backs with complex geometric patterns, dividing the circle into perfect segments and inscribing intricate webs of lines that demonstrated an intuitive yet advanced grasp of symmetry and proportion. Every planned city, every flowing tunnel, and every polished mirror stands as a testament to a civilization that saw the world through a lens of calculation, laying the geometric groundwork for the empire that would eventually consume them. High in the Peruvian Andes, the Chavin culture carved a temple complex from stone that functioned as a living, breathing engine of spiritual transformation. Chavin de Huanta is not a simple collection of buildings, but a multi-level labyrinth of precise engineering and psychological design. Its core is a honeycomb of underground galleries, dark passages that twist and turn without a single right angle. This disorienting geometry was entirely intentional. To navigate these corridors was to be stripped of your earthly bearings, guided by a master plan that used irregular shapes to create a powerful sensory experience. The engineering that made this possible was staggering. Deep within this stone maze, a network of ventilation shafts was cut with such accuracy that they maintained a constant flow of fresh air, preventing stagnation and allowing for the perpetual burning of ritual fires. Even more astonishing are the acoustic tubes, narrow channels built into the walls that could carry the sound of a conch shell trumpet from an inner chamber to every corner of the plaza outside. Creating these effects required a profound understanding of sound waves and air pressure, a form of physics expressed through perfect measurement. The entire site was a celestial instrument. The main temple structures were aligned with the rising and setting of key stars and constellations, anchoring the complex to the rhythms of the cosmos. A famous feature known as the lanzon is a towering, blade-like monolith of carved granite that stands at the exact center of the temple's cross-shaped galleries. During significant astronomical events, a beam of sunlight would pierce a strategically placed vent, illuminating this central deity figure in a dramatic display of light and shadow. This was not a lucky accident. It was the result of generations of precise astronomical observation, translated into stone. This calculative mind is further revealed in the intricate iconography that covers their stonework. The art of Chavin is a complex language of jaguars, eagles, and serpents, often shown in a state of transformation from human to animal form. These images are not random, they are built on a strict framework of symmetry and duality. The concept of complementary opposites like life and death or the human and spirit worlds was central to their belief system, and they expressed this philosophy through mathematical principles of balance and proportion. The famous Raimondi stone is a flat slab of granite carved with an image of a staff god. When viewed one way, you see a serene deity. but flip the stone upside down, and the same lines transform into the snarling faces of two other gods. This single piece of art is a masterpiece of duality and geometric precision. Its design so calculated that one set of lines serves two completely different visual purposes. The artists who created this were not merely craftsmen, they were geometers who understood how to encode deep cosmological ideas into a visual formula. Every twisted gallery, every echoing tube, and every transforming image was part of a grand equation designed to manipulate human perception and connect the physical world with the spiritual one. The Chavin did not just build a temple, they engineered an experience using mathematics as the hidden architecture of belief. Even the divine required precise measurements. The Hebrew Bible provides extraordinarily detailed blueprints for two of its most sacred structures, the portable tabernacle and Solomon's permanent temple in Jerusalem. The instructions specify every dimension down to the cubit, from the length of the altar to the width of the curtains, revealing a culture with a standardized system of measurement and a deep appreciation for geometric proportion. The very design was a mathematical act of faith, where perfect ratios in the physical world were believed to reflect the perfection of the divine. This was not arbitrary construction, it was calculated down to the last detail, implying a class of skilled artisans and scribes fluent in the mathematics of area, volume, and scale. This practical geometry was the foundation of their earthly kingdom as well. Managing a united monarchy required a sophisticated administrative mathematics. Scribes kept meticulous records for taxation, calculating the tithes of grain, wine, and oil that flowed into the royal storehouses. The military was organized by census, a massive undertaking of counting and grouping men of fighting age into thousands, hundreds, and fifties, a logistical feat that demanded a working decimal system and fluent arithmetic. This mathematical backbone allowed the kingdom to function, fund its projects, and field its armies. But perhaps the most stunning proof of their engineering mathematics is hidden deep underground. In the late 8th century before the Common Era, as the Assyrian army threatened Jerusalem, King Hezekiah ordered the construction of a life-saving water tunnel. This was not a simple ditch, it was a 533-meter-long conduit carved through solid bedrock, designed to bring water from the Gihon spring outside the walls into the fortified city. The engineering challenge was immense. Two teams of diggers started from opposite ends, hacking their way through the stone with only picks and hammers. How did they manage to meet almost perfectly in the middle? They used applied geometry. While we do not know their exact method, it likely involved a series of survey shafts dug from the surface to maintain a consistent, gentle downward slope. The Siloam inscription found in the tunnel itself celebrates the moment the two teams broke through, hearing the sound of each other's picks just before the water began to flow. This was a triumph of calculation over chaos, a life-saving project that would have failed with a single significant miscalculation in direction or grade. The mathematics of the Israelites, therefore, operated on two levels: the sacred geometry that built a house for God, and the practical engineering that saved a city from siege. The rugged peaks of the Armenian highlands presented a formidable challenge, but the Urartu kingdom met it with geometry and sheer force of will. Their massive stone fortresses were not built on convenient hilltops, but on sheer, inaccessible cliffs, deliberately chosen for their defensive superiority. Constructing these citadels required more than just moving multi-ton stones. It demanded a sophisticated understanding of structural engineering. The foundations had to be perfectly leveled on irregular bedrock, a task requiring precise angle measurement and load-bearing calculations to prevent the entire structure from sliding down the mountainside. The walls themselves were masterclasses in defensive geometry, built with strategically placed projecting towers that eliminated blind spots and created overlapping fields of fire for archers. Every stone was a piece of a three-dimensional puzzle, its shape and placement calculated to interlock with its neighbors, distributing immense weight and withstanding sieges for centuries. Yet their greatest mathematical legacy was not in war, but in water. In a landscape of extremes, the Urartu engineered a sprawling network of canals and artificial lakes to tame the arid climate. Their most famous achievement, the 70-kilometer-long canal stretching from the Hossap River to their capital at Tushpa, is a monument to surveying. To maintain a consistent, gentle flow over such a vast distance, engineers had to calculate the land's gradient with breathtaking accuracy, using simple tools like sighting poles and water levels to chart a course across valleys and hills. They carved channels directly through solid rock, their path a testament to a stubborn refusal to be defeated by geography. The system was a masterwork of hydraulic mathematics designed to control water pressure, prevent erosion, and distribute life-giving water across the kingdom. They even constructed massive artificial reservoirs, calculating their volume to store enough water to sustain cities through long dry seasons. The most astonishing part of this story is that some of these canals, built over 2,700 years ago, are still in use by farmers today. This is not a ruined relic, but a living, functioning piece of ancient mathematical genius, a seamless blend of calculation and survival that continues to quench the land. Cut directly into the living rock of the Anatolian highlands, the tomb of King Midas stands as a monument to Phrygian precision. Its facade is not a rough carving but a towering geometric masterpiece, its intricate patterns of interlocking triangles and meanders etched with a draftsman's control. This was more than decoration, it was a language of mathematics made permanent in stone, a testament to a culture that understood how to manipulate form and space on a colossal scale. The entire surface is a complex exercise in symmetry, each repeating motif calculated to maintain perfect proportion across the vast, uneven face of the cliff. This same calculative genius defined their urban world. The capital city of Gordian was not a haphazard settlement but a planned metropolis, its streets laid out in an organized grid that channeled traffic and defined residential and industrial quarters. The city's public works, including sophisticated drainage systems, required a deep understanding of gradients and volume to manage water flow and keep the streets dry, proving their math was as much about civic function as it was about sacred art. But the true source of the Midas legend was not gold but metal. The Phrygians were master metallurgists, and their renowned bronze and iron work was a triumph of applied mathematics. Creating a perfect bronze alloy was a chemical equation in physical form. Artisans had to calculate the exact ratio of copper to tin, a balance that, if wrong by even a small margin, would result in a metal that was too soft or dangerously brittle. They were solving for the ideal molecular structure long before the concept of a molecule existed. Controlling the furnace temperature was another precise calculation, a constant balancing act between fuel, air, and time to achieve the exact heat needed to pour flawless castings. This mathematical control over materials produced the famous bronze vessels and intricate fibulae, or safety pins, that became valued trade goods across the ancient world. Each object was proof of a formula successfully executed, a physical echo of the same geometric order they carved into their mountains. The legend of Midas may speak of a golden touch, but the reality was a culture with a far more valuable gift: the power to transform raw materials into works of art and engineering through the unerring application of mathematical truth. Carved into the summit of a sacred mountain, the city of Monte Albon was a feat of mathematical terraforming. The Zapotecs did not simply build on this high plateau, they reshaped it, slicing off the top of the mountain to create a vast, level plain as their foundation. This act alone required a staggering command of geometry and volume, calculating how much earth to move to achieve a perfectly flat surface for their grand plazas and pyramidal platforms. Every structure in this ceremonial center was then positioned with intention, its alignment a direct reflection of celestial order. The main platform of the complex was oriented to capture the zenith passage of the sun, that moment when the star is directly overhead and casts no shadow. On this day, the sun would shine straight down into a special chamber, marking a pivotal point in the agricultural cycle. This was not guesswork, it was precise astronomy made manifest in stone, a calendar built on a mountaintop. Their grasp of time was equally sophisticated, managed through a dual calendar system of profound complexity. The first was a 260-day ritual cycle, a sacred count that interwove 20-day signs with 13 numbers, creating a never-repeating sequence that governed ceremonies and divinations. Alongside this ran a 365-day solar calendar, tracking the seasons, but the true mathematical brilliance was in their combination of these two cycles. They meshed them together like interlocking gears, creating a larger 52-year calendar round. This meant that any specific date required a unique combination from both calendars to be fully identified, a system that demanded generations of meticulous astronomical observation and fluent arithmetic to maintain without error across centuries. This intellectual power was recorded in one of America's earliest writing systems. Zapotec glyphs carved into stone monuments include clear numerals, bars for 5 and dots for 1, and a rich array of calendrical signs, proving they were documenting history and cosmic events with a formalized mathematical language. The very layout of Monte Alban, with its perfectly aligned buildings and its ball court precisely situated according to cosmic principles, was a physical expression of this belief in a universe governed by number and cycle. The city was not just a place of power, it was a massive stone calculator forever tracking the relationship between the earth and the heavens. The heat of a Nigerian kiln held mathematical secrets within its flames. The Nok culture, flourishing over 2,000 years ago, left behind a legacy not in written texts but in breathtakingly naturalistic terracotta sculptures. Creating a life-sized human head from clay is an artistic challenge, but firing it without disaster is a profound test of thermal mathematics. These artisans were mastering the physics of heat long before it was a formal science. To transform wet, fragile clay into a durable terracotta masterpiece, they had to control their kiln temperatures with incredible precision. If the fire rose too quickly, the moisture inside the clay would turn to steam too fast, creating pressure and causing the entire sculpture to explode. If the temperature was not held at the exact right level for the exact right amount of time, the clay would not vitrify properly, leaving it weak and crumbly. They were solving a complex equation in real time, balancing the ratio of fuel to air, the mass of the clay, and the duration of the firing cycle through learned, empirical formulas passed down through generations. This was a hands-on understanding of thermodynamics, where a single miscalculation could shatter weeks of meticulous work. The evidence of their calculative mind is etched into the sculptures themselves. Look beyond the lifelike faces and you find intricate, repeated geometric patterns. Hairstyles are rendered not as solid forms, but as complex arrays of raised bumps and grooves arranged in perfect symmetry. Jewelry and adornments feature precise, interlocking shapes from concentric circles to parallel lines, all maintaining a consistent scale and proportion across the curved surface of the figure. This is not freehand decoration, it is the application of a formalized design system. The artists were using principles of geometry to plan these patterns, dividing the surface of the clay into segments and applying decorations according to a preconceived, balanced plan. This sense of harmony and order reveals a culture that thought in ratios, applying mathematical principles to bring beauty and structure to their art. This same practical intelligence fueled another, even more demanding industry. The Nok were among the earliest sub-Saharan Africans to smelt iron. The process of extracting metal from ore is a brutal chemical reaction that is utterly dependent on mathematical control. To achieve the high temperatures needed, they built furnaces that required a precise draft, a calculated flow of air to superheat the interior. They had to mix specific ratios of iron ore to charcoal, a recipe that, if followed incorrectly, would produce useless slag instead of workable metal. Every step, from the furnace's internal geometry to the timing of the extraction, was a variable in a life or death equation for their technology. The logistical mathematics of this operation were immense, involving the mining and transport of tons of ore, the production of vast quantities of charcoal, and the organization of skilled labor. The Nok terracottas are more than art. They are the silent, fired clay testimony of a culture that solved the most practical problems of survival and expression through an unspoken yet deeply advanced language of numbers. Their true power was not in conquest but in communication. The Arameans, a people scattered across the Near East, mastered the mathematics of language itself. Their greatest invention was a simple alphabetic script, a system so efficient it would become the ancestor of the Hebrew, Arabic, and even Greek alphabets. Before this, writing was a complex art, the domain of highly trained scribes who memorized hundreds of intricate cuneiform signs or Egyptian hieroglyphs. The Aramean alphabet broke this monopoly. It used a small set of around 22 simple letters, each representing a single consonant sound. Learning to read and write was no longer a lifetime study, a fact that democratized literacy and, most importantly, supercharged the world of commerce and administration. A merchant could now quickly jot down a contract, a tax collector could record tribute, and an official could send a detailed message across the empire. This was a mathematical leap in efficiency, reducing the complex symbols of older systems to a streamlined, logical code. This new tool for writing became the perfect vehicle for numbers. As Aramean merchants traveled their vast trade routes, their ledgers and contracts traveled with them, spreading not only goods but the mathematical concepts needed to manage them. Their documents detailed loans with calculated interest, partnerships with defined profit shares, and inventories with precise counts of goods. Because their script was so easy to learn, the mathematical knowledge contained within these records could be understood by a much wider audience, from the ports of the Mediterranean to the heart of Mesopotamia. The Arameans became the accountants and diplomats of the ancient world, and their language became the lingua franca of international business, the common tongue that allowed Assyrian, Babylonian, and even Egyptian traders to understand a single price or a shared contract. This placed them in a unique position as intellectual conduits. Operating freely between the great empires, Aramean merchants and scribes were the invisible network through which mathematical ideas flowed. A new algebraic technique developed in the courts of Babylon could be recorded in Aramaic on a scroll and carried by a merchant caravan to an Assyrian administrative center. A more efficient method for calculating the volume of a grain silo, perfected by Egyptian engineers, could find its way into an Aramean trade manual and then be adopted by planners in distant lands. They were not necessarily the original inventors of these advanced concepts, but they were the essential distributors, the ones who translated complex knowledge from one imperial language to another and disseminated it across borders. Their script was the universal file format of the ancient world, ensuring that a mathematical breakthrough did not die within one civilization but could be copied, shared, and built upon by others. In this way, the Arameans built an empire not of stone and soldiers, but of letters and numbers, weaving a web of calculation that connected the ancient world's greatest minds. Their legacy is written in stone, a language of power and proportion that defined classical Greece. The Dorians swept into the peninsula after the Great Bronze Age collapse, and their architectural vision was as severe and disciplined as their society. The Doric temple, epitomized by the Parthenon, appears as a monument of straightforward strength, but this simplicity is a grand and beautiful illusion. Every line you perceive as straight is actually a subtle curve. Every column that seems perfectly vertical leans inward with precise calculation. The architects engineered these optical refinements to counteract the tricks of human perception, ensuring their creations would look perfectly balanced and majestic from every angle. A building designed with rigid, geometric lines would actually appear to sag to the human eye, so they built curves into the very foundations and gave their columns a slight swell, a technique known as intosses, to create the visual impression of resilient, muscular strength. This was mathematics in service of beauty, a deep understanding of how we see the world translated into stone. The entire structure was governed by an unwavering system of ratios. The relationship between the column's height and diameter, the spacing between each column, and the proportions of the triangular pediment above were all determined by strict geometric formulas. Many of these proportions align with what we now call the golden ratio, a mathematical relationship where the whole is to the larger part as the larger part is to the smaller. This ratio, approximately 1.618 to 1, is found throughout nature and is inherently pleasing to the human brain. The Dorian architects did not leave behind complex equations, but they built this principle directly into their work, creating a harmony that feels both powerful and naturally right. This same mathematical discipline was the bedrock of their military dominance. The hoplite phalanx was not a mere crowd of soldiers, it was a living, breathing geometric form. Each heavily armored hoplite carried a large round shield, the aspes, designed to protect the man to his left. This created an interlocked wall of bronze and wood, a formation that was far more than the sum of its parts. For the phalanx to advance and maneuver as a single, unstoppable unit, every man had to understand his precise position within the geometric whole. They moved in perfect step, maintaining exact intervals and dressing their lines as if they were a single entity. The depth of the formation, whether 8 men deep or 16, was a calculated trade-off between pushing power and mobility, a logistical equation solved on the battlefield. The success of the entire army depended on this collective spatial mathematics, where a single soldier breaking rhythm could create a fatal weakness in the formation. The hoplite was both a warrior and a moving point in a grand geometric design, his life dependent on his neighbor's unwavering discipline and his own understanding of his place in the calculated order of the ranks. In the Doric column and the hoplite shield wall, we see the same core principle, a society that believed true power and beauty could only be achieved through rigorous, unyielding mathematical order. A gleaming lump of electrum found in a riverbed held the seed of a revolution. The Lydians, a powerful kingdom in western Anatolia, did not just mine this gold and silver alloy, they transformed it. By stamping pieces of electrum with a royal seal, they created the world's first official coinage, an innovation that would ripple across the globe. But this was far more than a monetary convenience. It was a monumental leap in applied mathematics. For a coin to be trusted, its value had to be consistent. This required a radical standardization of weight and purity, forcing the Lydian state to master the science of metrology. Royal mints had to develop precise scales and weights to ensure every coin contained the exact same amount of precious metal. They also had to solve the chemical mathematics of refining, calculating the exact alloy composition to guarantee the coin's intrinsic worth. A single debased coin could shatter public trust and collapse the entire system, so their calculations had to be flawless. This new, portable form of wealth ignited an explosion of economic mathematics. With standardized value, the concepts of fixed pricing, interest on loans, and currency exchange rates between Lydian staters and foreign goods became not just possible but essential. Merchants could now calculate profit and loss with unprecedented accuracy, while royal treasuries could model the flow of capital through taxation and state expenditure. The entire economy became a vast living equation, all running on the mathematical certainty embedded in each small, stamped disk. This same drive for precision defined their physical world. The Lydian capital, Sardis, was protected by an immense fortification system that snaked across the Acropolis. Its walls were not simple barriers, but complex structures built with projecting towers and angled gateways, each element positioned through careful geometric calculation to maximize defensive coverage and eliminate blind spots. Building these ramparts to withstand siege, engines required advanced load-bearing mathematics, ensuring the walls would distribute their own colossal weight without crumbling. Even in death, their calculative mind was evident. The monumental tomb of King Aliat's, father of the famed Croesus, is a giant earthen mound rising from the plain. Its construction was a feat of volumetric engineering, requiring planners to calculate the immense quantity of earth and stone needed to create this permanent landmark. The tomb's perfect circular base and consistent slope are a testament to a culture that measured and planned everything, from the weight of a coin to the dimensions of a king's final resting place. The Lydians proved that mathematics was the true currency of power, the invisible standard that built both economic empires and physical ones. A kingdom's wealth flowed not from gold but from the scent of sacred trees. The kingdom of Saba, the land of the legendary Queen of Sheba, built its prosperity on the frankincense and myrrh that were as valuable as gems in the ancient world. Controlling this lucrative trade required a mathematical mind of the highest order. Caravans laden with incense traveled hundreds of miles across the desert, and every step of this journey was a calculated risk. Sabaean merchants had to account for the weight and volume of their precious cargo, the supplies needed for the long trek, and the complex exchange rates between different regions. This demanded a standardized system of weights and measures that was trusted from the markets of Mesopotamia to the courts of the Mediterranean. Their entire economy was a vast living ledger, and its accuracy was the foundation of their legendary wealth. Yet this commercial empire would have been impossible without a far greater feat of engineering mathematics, the Marib Dam. This was not a simple wall of stone, it was the heart of the Sabaean civilization, a massive earthen structure that harnessed the violent, seasonal floods of the Wadi Dana. To build it, engineers performed staggering calculations of volume and hydrology. They had to determine the exact quantity of earth and stone required to create a barrier strong enough to hold back a torrent of water, and then design a spillway system to release that water in a controlled, manageable flow for irrigation. The geometry of the entire structure, from the slope of its embankments to the precise angles of its sluice gates, was a masterpiece of applied mathematics designed to withstand the immense pressure of the reservoir. The dam's true genius, however, lay in its longevity. It did not just function for a few decades, it sustained agriculture in the region for over 1,000 years. This was not luck, it was the result of perpetual, precise maintenance. A specialized class of engineers was responsible for constantly monitoring the structure, calculating the erosion of its stone components and the silt buildup in its reservoir. They used their advanced understanding of geometry to plan and execute repairs, ensuring the dam's integrity generation after generation. This single, calculated structure turned the desert into a garden, supporting a population large enough to manage the incense trade and build magnificent cities like their capital, Marib. The kingdom's prosperity was quite literally channeled by mathematics, a testament to a civilization that understood that controlling water was the first step to controlling commerce, and that both required an unerring command of numbers. The Medes forged an empire with logistics as their primary weapon. Rising to power in the highlands of ancient Iran, they demonstrated that controlling a vast territory was less about constant battles and more about the mathematical precision of its administration. Their genius lay in creating a framework so effective that it became the blueprint for the first Persian Empire that followed them. To govern diverse lands and peoples, they needed a system for resource allocation and taxation that was both fair and ruthlessly efficient. This required a standardized system of weights and measures, and scribes capable of complex arithmetic to calculate tribute from every province, turning the chaotic flow of wealth into a predictable, manageable stream that fueled the imperial machine. This organizational mathematics found its ultimate expression in their legendary capital, Ecbatana. Ancient historians like Herodotus described it as a city of 7 concentric walls, each painted a different color and rising toward the central citadel where the royal palace stood in gleaming gold. Whether this was a literal architectural plan or a powerful symbolic representation, the concept itself reveals a mindset obsessed with geometric order and hierarchical structure. A city designed in perfect circles is a feat of immense surveying and planning, requiring a masterful grasp of geometry to lay out the foundations and calculate the staggering amounts of material needed for each successive ring. This was urban planning as a statement of power, a physical manifestation of a society that saw itself as the ordered center of the world. Their military might was equally dependent on calculation. The Medes were pioneers of siege engineering, and their armies moved with a logistical precision that overwhelmed their enemies. Building the ramps and towers needed to assault fortified cities was an exercise in real-time volumetric mathematics. How much earth and timber was required for a siege ramp 50 feet high? How many days would it take 10,000 soldiers to construct it? The answers to these questions were not guesses. They were the products of a refined military science that could project force with mathematical certainty. From the concentric rings of their capital to the disciplined columns of their army, the Medes proved that the true architecture of empire was not built of stone alone, but of numbers. Beneath the stark desert of southern Peru, the Paracas culture wove their understanding of the cosmos into fabric. Their famous textiles are not merely cloth, they are complex geometric theorems rendered in vibrant thread. Each blanket and mantle displays an explosion of intricate patterns, from interlocking stepped frets to perfect concentric circles, all woven with a precision that defies belief. The creation of these designs required more than artistic skill. It demanded a masterful, pre-planned mathematics. The weavers had to calculate the exact count of threads for each color changed to maintain perfect symmetry across the entire piece. A single miscalculation in the pattern's repetition or proportion would have thrown the entire intricate design into chaos, resulting in a tangled, asymmetrical mess. This was mathematics made tactile, a coded language of ratios and sequences mastered by artisans who thought in grids and angles long before they ever touched a loom. This same sense of celestial order guided their rituals for the dead. Their subterranean necropolises, collective tombs carved into the dry earth, were not random holes in the ground. These burial chambers, filled with mummy bundles swathed in those magnificent textiles, were often aligned with significant astronomical events. The entrance shafts and internal layouts were oriented to capture the rays of the solstice sun or to frame certain constellations visible in the clear desert night. For the Paracas, the journey into the afterlife was a passage mapped by the stars, and their tombs were the architectural calculators that ensured the deceased would navigate it correctly. This profound connection between the earth and the sky may find its ultimate expression in the nearby Nazca lines, while later in time, many scholars see a direct cultural and technological link to the Paracas. The immense geometric figures and perfectly straight lines etched into the desert pavement are a staggering feat of surveying. To create a kilometer-long straight line across broken terrain, or to plot a perfect spiral or a massive hummingbird visible only from the air, the creators needed an advanced, practical command of geometry. They likely used a series of stakes and ropes, employing simple yet brilliant triangulation techniques to scale up small models into gigantic desert drawings without losing the proportions. The same mathematical mind that could precisely plan a complex textile pattern on a loom was capable of projecting that pattern onto a landscape of epic scale. Each straight Nazca line is a testament to their ability to calculate angles and maintain direction over vast distances, while each biomorphic figure showcases a genius for scaling complex forms with unerring accuracy. From the microscopic precision of a single thread to the monumental scale of a desert geoglyph, The Parakas and their successors demonstrate that their world was bound together by an invisible grid of mathematical relationships, a calculated harmony between the woven, the buried, and the drawn. Their stone walls snaked across the Balkan hilltops, a puzzle of colossal boulders fitted together without mortar. The Illyrians built for endurance, and their so-called Cyclopean fortifications were a masterclass in structural mathematics. Each multi-ton stone was an irregular polygon, and the builders had to calculate the precise angles and load-bearing points for every single one, ensuring that the weight of the entire wall was distributed perfectly to create an immovable whole. This was not brute force, it was a three-dimensional geometric problem solved on a monumental scale, resulting in fortresses that have withstood millennia of earthquakes and conflicts. This same calculative precision defined their sacred spaces. The burial mounds of Illyrian nobles, known as tumuli, were not simple piles of earth. They were complex, layered structures built with stone schist tombs at their heart, all covered by a precisely measured cone of soil and rock. Constructing a stable, symmetrical tumulus required a clear understanding of volume and geometry to prevent the mound from slumping or eroding unevenly over time. Each of these mounds was a permanent geometric signature on the landscape, a calculated monument to the dead. The Illyrian mind for mathematics burned hottest in their forges. They became renowned for their advanced metalwork, particularly with silver and bronze. Creating a perfect bronze alloy is a chemical equation, a delicate balance of copper and tin that must be calculated to the exact ratio. Too much tin and the metal becomes brittle, too little and it remains soft. Their smiths had internalized this formula, controlling their furnace temperatures with an intuitive grasp of thermal dynamics to produce weapons, tools, and magnificent ornaments of consistent strength and beauty. This mastery is etched into the artifacts they left behind. Intricate bronze belts and silver fibulae are decorated with precise geometric patterns, spirals, concentric circles, and meanders that repeat with perfect symmetry. These are not random scratches, but a formalized system of design, a language of shape and ratio that conveyed meaning and status. Some of these symbols, found stamped onto clay or metal, may even represent an early system of accounting marks or proto-writing, used to track goods, denote ownership, or record transactions. A spiral on a bracelet was more than decoration. It was the expression of a culture that understood the world through measured forms and calculated relationships, from the grand scale of their hill forts down to the fine details on a piece of jewelry. Deep beneath the Austrian Alps, the Celts of the Hallstatt period were solving complex engineering problems in total darkness. Their wealth was not gold, but salt, a mineral as precious as any metal, and they went to incredible lengths to extract it. They dug shafts hundreds of feet deep into the unstable rock of the Durenberg mountain, a task fraught with the constant danger of collapse. Their solution was a masterpiece of structural mathematics, a system of intricate timber framing that braced the tunnels and shafts from within. This was not random shoring up. The carpenters had to calculate the precise angles and load-bearing capacities for every wooden beam, creating a three-dimensional lattice that could withstand immense pressure from all sides. They were essentially building an inverted wooden skeleton inside the mountain, a feat that required a profound, practical understanding of geometry and physics to keep the earth from swallowing them whole. This mathematical mind extended to the surface, where a vast logistical operation unfolded. The raw salt rock had to be hauled up the deep shafts, a process demanding calculations of weight, pulley systems, and human labor. Then came the transportation, moving tons of this white gold across the treacherous Alpine passes to trade routes that stretched across Europe. Organizing this supply chain, from the depths of the mine to distant markets, was a triumph of early logistical mathematics, ensuring the Hallstatt culture's prosperity and influence. The same precision that secured their mines was stamped onto their personal possessions. Hallstatt metalworkers produced jewelry and weaponry of stunning geometric clarity. Bronze fibulae or brooches were not merely functional, they were exercises in perfect symmetry, their arcs and spirals balanced with a draftsman's accuracy. Sword hilts and dagger blades were often inlaid with intricate patterns of circles and lines, each element spaced according to a strict, repeating ratio. This was not freehand decoration. The artisans worked from a mental blueprint of harmonious proportions, applying a formalized system of artisan mathematics to create objects that were both beautiful and symbolically powerful. This calculative approach to order shaped their entire world. Their fortified hilltop settlements, known as oppida, were not chaotic villages. They were planned communities, their layouts revealing a clear sense of social organization and spatial mathematics. The defensive walls followed the contours of the hill, but their construction was methodical, requiring calculated volumes of earth and timber. Inside, the placement of chieftains' longhouses, workshops, and storage pits suggests a society that understood how to allocate space for efficiency, security, and social hierarchy. The Hallstatt Celts proved that mathematical thinking was not confined to the Mediterranean sun, but was alive in the heart of Europe, governing everything from the terrifying darkness of a salt mine to the gleaming symmetry of a bronze brooch. The Neo-Assyrian Empire elevated calculation into an instrument of absolute power. Under kings like Sennacherib, their building projects reached a scale that defied belief, each one a testament to a bureaucracy fluent in advanced mathematics. His palace at Nineveh was not merely a royal residence, it was an administrative engine, and its very existence was made possible by a water supply system of staggering ambition. The aqueduct at Jerwan, built by Sennacherib, stretched for 50 kilometers, channeling water from the mountains to the heart of the capital. This was not a simple ditch. Its builders engineered a stone channel with a precise, consistent gradient, allowing water to flow steadily across hills and valleys. They even constructed a massive stone aqueduct to span a river, a structure requiring masterful calculations of load, arch support, and hydraulic pressure. This was engineering mathematics on a grand strategic scale, solving the problem of sustaining a metropolis of over 100,000 people. The logistics behind such a project are themselves a mathematical wonder. How many thousands of laborers were required? How much food and water did they need daily? How were tons of stone quarried, transported, and fitted? The royal administration had to solve these equations of workforce management, calculating rations, schedules, and material transport with chilling efficiency. This calculative precision was the empire's lifeblood, visible even in the intricate stone reliefs that adorn the palace walls. These carvings do not just show scenes of conquest and lion hunts. They depict the meticulous administration that made those conquests possible. Scribes are shown intently at work, holding not just writing stylely but measuring rods and scales. They are quantifying the spoils of war, counting prisoners, weighing tribute of gold and silver, and measuring parcels of land. In these images, mathematics is portrayed not as an abstract study, but as the essential tool for inventorying an empire, for turning chaos into taxable, manageable order. Every captured city, every subjugated people was entered into a vast imperial ledger, their worth calculated down to the last shekel. This obsession with measurement was the ultimate expression of royal power. Monumental architecture was designed to overwhelm the senses, its sheer scale a psychological weapon. The precise angles of a ziggurat, the intimidating symmetry of a city gate, the perfect alignment of a processional way, all were calculated to project an image of unshakable divine order. The message was clear: a state that could measure the heavens and move mountains with its math was a state that could not be challenged. The empire itself was a machine, and mathematics was the language of its operation. Long before the Caesars, the practical genius of Rome was already being forged in clay and law. The early Romans of the kingdom and republican eras were not abstract mathematicians, but they were masterful engineers whose entire society was built upon a foundation of rigorous calculation. They looked at the world and saw problems to be solved with measurement and order. Their first mathematical language was borrowed from their sophisticated northern neighbors, the Etruscans. They adopted the Etruscan numeral system, a straightforward tally method using symbols like I for 1, V for 5, and X for 10. While not a place value system like our own, its clarity and efficiency made it a powerful tool for the administration of a growing city-state. It was perfect for recording laws, counting soldiers, and marking the boundaries of property, turning the chaos of a burgeoning society into a ledger of clear, accountable numbers. This calculative mindset found its most profound expression in the division of the land itself. As Rome expanded, it needed a way to distribute conquered territory fairly among its citizens and veterans. The solution was centuriation, a system of land surveying of breathtaking geometric precision. Surveyors, known as agrimensors, would first establish two main perpendicular lines, the Cardo running north-south and the Decumanus running east-west. From this central cross, they would lay out a perfect grid of squares, each measuring approximately 700 meters on a side. This was not a vague approximation. Using a simple but brilliant instrument called a groma, a cross-shaped device with weighted plumb lines, they could sight perfect right angles across vast, uneven landscapes. Every plot of land within this giant grid had a defined, calculable area, making taxation straightforward and property disputes rare. The entire countryside was transformed into a geometric proof of Roman order, a physical manifestation of their belief that law and land were inseparable. This same engineering audacity was channeled underground. The Cloaca Maxima, or Great Sewer, began as an open canal to drain the swampy valleys between Rome's hills. But the Romans soon enclosed it, creating a massive, vaulted stone tunnel that channeled the city's waste into the Tiber River. Building such a structure required a masterful grasp of hydraulics and volume. Engineers had to calculate the precise gradient of the sewer's floor to ensure a constant, self-cleaning flow of water, strong enough to carry away debris but not so steep as to cause destructive erosion. They were solving complex problems of flow rate and friction centuries before these concepts were formally defined. The Cloaca Maxima was more than a sanitation project. It was a declaration that even the most fundamental aspects of nature could be bent to the will of Roman calculation. That will reach its next logical conclusion with the Aqua Appia, Rome's first aqueduct. Completed in 312 BC, it was a 16-kilometer-long underground channel that brought fresh, clean water from distant springs into the heart of the city. Its construction was a staggering feat of surveying. To maintain a consistent, gentle downhill slope over such a long distance, the engineers had to chart a course through hills and valleys with incredible accuracy. They used simple tools like chorobates, a long, water-leveled table, to ensure the channel lost elevation at just the right rate. A miscalculation of even a fraction of a degree would mean the water would either stagnate or flow with too much force and burst its conduit. This project, like the sewer and the surveyed fields, was not born from imperial vanity. It was the work of a pragmatic republic, a society that understood that its strength and health depended on a relentless, practical application of mathematics to the world around them. The legions and the Colosseum were still far in the future, but the mathematical mind that would build them was already wide awake, laying the invisible groundwork for an empire. A nomad's life on the open steppe was a masterclass in applied mathematics. The Scythians, a fierce confederation of horseback riders who dominated the Eurasian plains, carried their mathematical genius not in clay tablets, but in the very fabric of their daily survival and their most sacred art. Their mastery began with the land itself, a boundless sea of grass where managing vast herds of horses, cattle, and sheep was a constant logistical puzzle. How do you calculate the grazing capacity of a valley for 10,000 animals? How do you coordinate the migration of entire clans across thousands of miles? ensuring you arrive at the next seasonal pasture with your people and livestock intact. The Scythians solved these equations of movement and resource allocation with an intuitive yet sophisticated spatial mathematics, reading the landscape like a living map and navigating by the stars to maintain a precise annual rhythm of life. This logistical brilliance was encapsulated in their portable home, the yurt. Its circular lattice wall and radiating roof poles were a geometric marvel, a structure designed for both rapid assembly and incredible resilience against the steppe winds. The entire dwelling was a lesson in modular engineering and perfect symmetry, its dimensions calculated to create a spacious, stable interior that could be packed onto a cart and moved at a moment's notice. This same calculative precision was forged into their weapons. The famed Scythian composite bow was not a simple piece of curved wood. It was a laminated weapon of wood, sinew, and horn, engineered with a precise recurve shape that stored immense energy. Crafting this weapon required an intimate understanding of material properties and geometry, calculating the exact angles of the curves to maximize power and range while keeping the bow compact enough to fire from horseback. But the ultimate expression of Scythian mathematics lies buried in their royal kurgans, the great burial mounds that dot the steppe. Within these earthen tombs, archaeologists have found gold work of such intricate detail it seems impossible for a nomadic culture. Their famous animal-style art, depicting stags, panthers, and griffins in dynamic, contorted poses, is a symphony of geometric order. Each creature is composed of interlocking curves and spirals, its body parts perfectly balanced and proportioned according to a strict, repeating system of ratios. This was not free-form artistry, it was a coded visual language built on a deep understanding of form and symmetry. The creation of these objects was a feat of metallurgical mathematics. Scythian goldsmiths had to calculate the exact temperatures needed to smelt and work the metal without melting or cracking it. They perfected the art of granulation, fusing microscopic spheres of gold onto a surface to create textured patterns, a process demanding absolute control over heat and a precise chemical understanding of the alloys involved. Every golden stag, with its limbs folded into perfect geometric arcs, is a testament to a culture that saw the world through a lens of calculated motion and balanced form, proving that the most profound mathematics could be carried in a saddlebag and worn as a badge of honor. In the quiet monasteries of ancient India, a tradition of thought was pushing the boundaries of the human mind toward the infinite. The Jain mathematicians, ascetic scholars of the first millennium before the Common Era, were exploring concepts so abstract they would not be fully grasped in the West for over 2,000 years. Their work was not driven by the need to build pyramids or tax grain, but by a profound philosophical quest to understand the nature of the cosmos, the soul, and reality itself. They grappled with the idea of the limitless, contemplating different types of infinity with a sophistication that feels startlingly modern. They categorized numbers in elaborate ways, distinguishing between countable, uncountable, and infinite sets, laying the early groundwork for what we now call set theory. They formulated basic laws of indices, understanding that a number raised to a certain power could be manipulated mathematically, a fundamental principle of algebra. Their classifications of numbers were incredibly detailed, sorting them into categories based on whether they were even or odd, prime or composite, or could be arranged in specific geometric forms. They even delved into the mathematics of permutations and combinations, calculating the number of ways objects or philosophical principles could be arranged and rearranged, which they saw as a way to map the possible variations of existence. Perhaps most astonishingly, their texts show an early understanding of the concepts that would lead to logarithms, exploring the relationships between arithmetic and geometric progressions. This was not mathematics for building or trading. It was mathematics for contemplating the architecture of the universe and the vast, innumerable multitude of souls within it. Their abstract genius demonstrates that the history of math is not a single river, but many streams, and that one of the most powerful flowed from a tradition of pure philosophical inquiry that sought to measure the immeasurable and count the uncountable. An empire's true power lies not just in its conquests, but in its ability to unify them under a single, calculable order. The Persian Achaemenid Empire achieved this on an unprecedented scale, becoming a grand synthesizer of the ancient world's mathematical knowledge. After conquering civilizations from the Egyptian rope stretchers to the Babylonian algebraists, the Persian kings did not discard their learning. Instead, they created a universal standard, a common language of measurement and engineering that bound their diverse territories into a cohesive whole. They standardized weights and measures across the empire, ensuring that a silver shekel minted in Sardis held the exact same value as one spent in Babylon or Memphis. This mathematical consistency was the bedrock of imperial trade and taxation, transforming a patchwork of kingdoms into a single, manageable economic unit. The sheer genius of this synthesis is most vividly expressed in a ribbon of stone and packed earth known as the Royal Road, stretching over 2,700 kilometers from the heart of Persia to the coast of Anatolia. This was not a simple dirt path. It was a meticulously engineered highway, a feat of logistical mathematics that would not be rivaled for centuries. Surveyors had to calculate its course across mountains, rivers, and deserts, maintaining a consistent, gentle grade that could be traversed by royal messengers and trade caravans alike. Along its length, they positioned 111 relay stations at precisely calculated intervals, each stocked with fresh horses and supplies. This network allowed a message to travel the entire distance in just 7 days, a speed unimaginable before. The mathematics behind this system was staggering, requiring planners to solve for the optimal spacing of stations, the daily range of a horse, and the supply chains needed to keep every outpost provisioned. It was the internet of its day, a physical network whose speed and reliability were born from flawless calculation. This same imperial mathematics reached its zenith in the ceremonial capital, Persepolis. Here, the empire's architectural vision was carved into the side of a mountain. The vast Apadana, or audience hall, was supported by 72 intricately carved stone columns, each standing over 20 meters tall. Arranging these colossal pillars to support a massive cedar roof required breathtaking precision in their placement and alignment. Every column base had to be set at the exact same level, and every shaft had to be perfectly vertical, a task achieved with advanced surveying tools and geometric principles. But the true engineering marvel lay beneath the stone floors. Archaeologists have uncovered a complex subterranean water supply and drainage system that channeled rainwater away from the grand plazas and terraces. This network of tunnels and canals, built with a precise, consistent gradient, prevented flooding and erosion, ensuring the monumental city would endure. The builders of Persepolis were not just working from one tradition, they were applying the combined hydrological knowledge of Egypt, Mesopotamia, and beyond, solving problems of volume, flow, and pressure on a scale worthy of a world empire. In the standardized shekel, the measured pace of the Royal Road, and the perfect geometry of Persepolis, the Achaemenids demonstrated that the ultimate expression of power was the ability to measure, to calculate, and to impose a beautiful mathematical order upon the entire known world. Across the Aegean Sea, a fundamental shift was taking place in the very nature of thought. The pre-Socratic philosophers of ancient Greece began to ask a new kind of question, one that would transform mathematics from a practical tool into a pure science of the mind. They looked at the same geometric shapes and numerical relationships that the Egyptians and Babylonians had used for millennia, but they saw something different, not just a means to an end, but an eternal truth waiting to be discovered through logic alone. This was the dawn of theoretical mathematics, a revolution in human understanding. Thales of Miletus, often called the first Western philosopher, exemplified this new approach. He used geometry to solve practical problems, famously calculating the height of the pyramids by measuring their shadows at the time of day when his own shadow was equal to his height. But his true legacy lies in what he did next. Thales is credited with formulating the first mathematical proofs, deductive arguments that established geometric truths not through measurement but through irrefutable logic. He proved that the angles at the base of an isosceles triangle are equal and that a circle is bisected by its diameter. These were not just observations, they were universal statements, true for all triangles and all circles everywhere and forever. This was the monumental leap from knowing how to build something to understanding why it must be so. This intellectual revolution found its most famous champion in Pythagoras and the secretive school he founded. The Pythagoreans took the concept of number and elevated it to a cosmic principle. For them, numbers were not just for counting, they were the ultimate reality, the abstract building blocks of the universe. They discovered profound mathematical relationships in music, finding that the harmonious intervals of a lyre's string corresponded to simple whole number ratios. This convinced them that the entire cosmos was governed by number, a concept they called the harmony of the spheres. Their most enduring contribution, of course, is the theorem that bears the founder's name. While the Babylonians had used Pythagorean triples in their calculations 1,000 years earlier, the Greek contribution was different. The Pythagoreans sought not just a useful rule, but a universal, proven truth. They provided a logical demonstration, a geometric proof that in any right-angled triangle, the square on the hypotenuse must always equal the sum of the squares on the other two sides. This was a statement about the very fabric of space itself, proven to be eternally and unchangeably true. This shift from application to abstraction marked a pivotal moment in human history. The pre-Socratics established the idea that mathematical truths exist independently in a perfect, conceptual world, and that the human mind, through pure reason, could discover them. They laid down the rules of the game, the deductive framework that would become the gold standard for all mathematical and scientific inquiry to come. In doing so, they built the intellectual stage upon which giants like Euclid would systemize geometry and Archimedes would pioneer physics, forever changing our capacity to comprehend the universe. From the Sumerian base 60 system to the abstract infinities of Jain philosophy, this journey reveals a stunning truth. Advanced mathematics was not a single spark that ignited in one place, but a constellation of genius that flared up independently across the globe, from the deserts of Peru to the plains of China. These 35 civilizations did not simply count and measure, they engineered impossibly precise calendars, calculated the orbits of planets, and proved geometric theorems, all to solve the fundamental human problems of survival, power, and meaning. The pyramid and the yurt, the coin and the loom, the aqueduct and the oracle bone, all stand as monuments to this universal human drive to find order in chaos through numbers. Our modern world of satellites, finance, and architecture does not rest on a single foundation. It is built upon a shared intellectual heritage, a collective inheritance of discovery that belongs to all of humanity. This was never a European invention, but a global conversation in the language of mathematics, a tool as essential to our ancestors as it is to us. We have walked with the rope stretchers of Egypt and the weavers of Paracas, the merchants of Phoenicia and the philosophers of Greece. Now we want to walk with you. Which of these ancient mathematical masters left you in awe? Was it the Babylonians solving quadratic equations on clay, or the Minoans with their geometric art and hydraulic engineering? Share the civilization that most surprised you in the comments below, and join us as we continue to uncover the hidden equations that wrote our history.